attend this conference. And here I have a subtitle here. Here's a story. When I came here to have lunch with my good friend Alex on Monday noon, and he told me, according to his knowledge, decentralized is not popular right now. Okay, that make me to think about the change point. Okay, decentralized means to transform the raw data to binary data, because due to the information technology, people just transfer directly. Well, say that give me a discourage. So I think possibly it's time to change. Then I asked one of the organizers, John Austin, if I could change the title. He said, okay, because this is a change point conference. Okay. Okay, in order to make this not abrupt change, I try to do some local smoothing. Okay, because this term is not useful, so I erase it. Then the quick change detection becomes applications. Then the sensor networks becomes multidimensional. So only one keyword left, hidden Markov models, and hopefully I will make non-trivial connection between hidden Markov model and these problems. Okay, I write a hidden Markov model here. Called hidden Markov chain. Right. Indeed, we try to solve these problems around 2011 with my PhD students, Michael Gao. And we had a very nice discussion with Davey, and when he was in Taiwan. And hopefully we will try to make a non-trivial extension of his early work. Here is the agenda. I will give motivation and literature review, and then our approach. We try to view the simple random walk as a Markov chain in a non-trivial way. Then state our main results and try to implement the result by doing numerical simulation and give one financial applications, then conclusion, and the future works. And I hope this approach can be applied to nonlinear time series. Okay, not make a connection to other group of the audience. Okay, here's the motivation first. It's a multidimensional Q-sign. One type of multidimensional Q-sign is to simultaneously use several Q-sign procedures. That means we have D+1 Q-sign procedures, and each one is defined as the first stopping time of this statistic close a linear boundary. Then the multidimensional Q-sign is defined as the minima of the D+1 stopping time. Okay. And probably I don't have to illustrate Q-sign because, okay. Then we know multidimensional Q-sign procedure are commonly used in industrial statistics, signal process, and other fields. Now here are reference. So the quantity of interest here, we want to approximate the probability of a false alarm, that's under null, and the average detection delay under alternative. Okay, that's the goal. We try to develop a mathematical approximation of these two quantities. Okay, here is the idea. Okay, let's start with Tarkovsky there, and we try to rewrite the stopping time as a simple, one-dimensional simple random walk, then plus throwing change term. Okay, now here is a multi-dimensional case. Still, we have maxima of each one plus throwing change terms. Okay, that's the stopping time for MQ sign. Okay, then we forget about this term to make life simple at this moment. That's a simple version of MQ sign. By only consider the principal part of this one, then the problem, can we transform this to a general setting like this one? And this will be described in motivation 2. Okay. Here is consider another motivation. Okay. Here's a correlated defaults. We want to modeling correlated defaults. People use multi-dimensional simple random walks. For instance, in the Mertens model with geometric Brown motion, this is a discretization of that one, the multi-dimensional simple random walk. Then the default time of the ith firm is to be defined to be the first time of this quantity less than a linear boundary, negative b. And this reference for pricing concern, like first to default. Okay, one consider the joint default probability to be defined as a minima of d plus 1 stopping time less than n. Okay, we are interested to approximate this quantity. Okay, then here is a little mathematics. We can rewrite this one to be less than b as this quantity to be less than negative b, and this becomes Sn minus h of Tn greater than b. Here Sn is negative Vn1, belongs to the first one-dimensional. This one has positive drift. And the Tn is d-dimensional. This one has mean 0. And h is a function like this one. Okay, that means the stopping time can be rewritten as, oh, this is infima of n, such that this quantity happens. Okay, the third motivation is from multiple sensor problems. Here reference by Tarkovsky, Baraja, Mei Yajun, and Xie and Sigma. Okay, here is one possible stopping time is defined as these quantities. Okay, by using law of large numbers, then we can give a simple version of that one to be defined as this quantity, which is bigger than this linear boundary. This is nothing but like the Q-sign setting. That means we can approximate this stopping time by using this framework. Okay, so here I just give 3 motivations. One is from MQ sign. The second one is from the Fourier default. The third one is from multiple sensor. Okay, here is the general framework. We want to try to consider the stopping time in this way. That Sn is a simple random walk, one-dimensional simple random walk with positive drift, and Tn, this should be d-dimensional zero drift simple random walk, and h is Rd to R1. It's a nice function. Okay, I mean, we want to consider this multi-dimensional boundary crossing probability motivated by 3 applications. Okay, so here we try to provide a limiting distribution of tau n for this ruin probability and expected value of this one in second order things. Okay, as b goes to infinity. Okay, here is the goal. Okay, I just give a brief review of the literatures. There are one-dimensional process with a linear boundary, the early 60, sigma, and many others for simple random walk. Me and Lai and myself considering Markov random walk. The one-dimensional process with nonlinear boundaries, the 4 seminar papers by Woodruff, Lai, and Sigma, 2 papers, and Zhang Chunhui's PhD dissertation. And me and my PhD students, we try to extend to Markov random walk. Okay, and then we have a multidimensional process with linear boundary, Carson and Kinner, me and Professor Lai, and multidimensional with nonlinear boundaries, this one, this key, consider non-homogeneous random walk existing in a core. Okay, here is the general idea. Okay, the idea is this one. Because h of t0 starts 0, and h of 0 is assumed to be 0, and I just add this term without changing anything, right? I have this quantity, I rewrite this one as un, and un is this one, as zk. This becomes varying drift problems. Okay, so we have un to be a summation of zk, and here jk is nothing but a couple of d-dimensional simple random walk. This is Markov chain. Okay, everybody knows, right? Then the varying drift can be captured by Markov chains. Okay, so here I try to make the hidden Markov model. Here is my understanding for hidden Markov chains. So here we have Markov chains, right? Called chain is a Markov chain. But we do not observe chain. We observe nonlinear function of chain. Here is a chain. This is hidden Markov model. This is good for mathematical theory. This is good for modeling. But the difficulty is this is not a Markov chain. So it's difficult to analyze or compute. So, okay, to make life simple, so people just put these two together in a non-trivial way, right? So this people started this one very early in 1940 by Kai-Lai Chang and Ron Bike. Then the 60 by Bain, and the 80 by Rabiner for speech recognition, etc. I call this is Markov random walk. Right? So this is good for modeling. This is good for mathematics. We put them together. I hope to catch both. Okay. Now this is, so from mathematical point of view, this is a Markov chain. But this is not a Markov chain. Right? This is Markov chain in a large space from mathematical point of view. But from computational point of view, if I put it here, by some kind of plug-in principle, this is called filtering method, right? Okay. So instead of consider modeling, in my previous the talk, I consider this one as a mathematical device to treat this problem. Okay, that means we consider this is a one-dimensional Markov random walk. Okay, so the tau n becomes the one-dimensional Markov random walk close a linear boundary. Okay. Okay, the problem becomes giving a one-dimensional Markov random walk. How do we approximate, for instance, this one? This already been done by me and Professor Lai. Consider this one. Okay, this is nothing but the first order approximation. This term reflects the overshoot because of discretization. And this is due to the Markovian dependence. If the initial state is from the invariant measure, then this term cancels out. Okay, and this quantity is from the Poisson equation governed by the Markov chain. Okay, that means this is a boundary, this is overshoot, this is Markovian dependence. Okay, that means the life seems to be perfect. Okay, but fortunately or unfortunately, we all know from the first course in probability theory, Tn minus 1 Tn is a simple random walk. For zero drift simple random walk, they are always null recurrent. Even worse or better, when the dimension is greater than 3, this is transient. Right? That means the whole Markov chain theory cannot be applied to this Markov chain. Okay? So here is the idea. Okay. Just to do truncation, we learned this one, right? Truncate. This is main direction. This is other directions, zero drift direction. So I truncate the state to be compact, right? Then the Markov chain is within this compact. But the problem, we got to lead to let this truncation goes to infinity, right? But fortunately, we are considering boundary crossing problems. That means I can try to let this truncation goes to infinity in a suitable way, such that this simple random walk hit boundary before the truncation goes to infinity. That's the simple idea. Okay, the idea is rather simple, but the technique is rather difficult. Okay, here's a simple idea. Okay, only 10 minutes, so probably I got to skip most the technical part. Okay. Here, because we're doing truncation and then let it goes to infinity, we need a sequence of Markov random walk. It's some kind of renew theory for Markov random walk. Okay. Here are conditions. Probably I don't have time to go through the whole conditions, but I'll give you examples. A reasonable example satisfy these conditions. Okay. The crucial one, this one, we are considered nonlinear boundary, but hopefully we are in piecewise linear. That means I can chart the whole state space by piecewise linear. Eventually, the piecewise linear with probability pk to state one region of linear boundary. Okay. Now here is the result. Okay. I want to approximate this quantity multiplied by mu. Then this is first order approximation. This is two extra terms. The Laplace refract the overshoot terms. But here we have k regimes with probability pk. Okay, and this quantity related to the overshoot part. Okay, and this is nothing but h function of multivariate normal distributions. Okay, so this is computable. It's not easy, not difficult to compute. And this, for this term, we probably need to compute by Monte Carlo. But this is better than the crude Monte Carlo, because the crude Monte Carlo is a simple path, right? Because whole simple path close a boundary. But this one is a first later, which doesn't consider first time to close 0. Okay, so the computational time is much more less for this case. Okay, so we have some kind of I won't say neat result, but a reasonable computable result. Okay, this is a function applied to multivariate normal. This is overshoot. Okay, and then here is Lewin probability. Simply forget all these parts. All these parts are to make life difficult. Okay, if the boundary is smoothing, so this is 0, this is 0, this is rate of convergence. So this is nothing but multivariate normal distributions and evaluated for each time. So this is not difficult to compute. Okay, compute multivariate normal distributions. Okay. Here are examples. Satisfy the result. We consider a boundary. Here we only consider infinite norm. But this is finite dimension. So without loss of generality, this can be generalized to any norm. Okay, for beta, it's less than 1. Okay, sublinear polynomial and the linear terms. And the maxima of all of these quantities. Thus, 3 examples satisfy our theorem. Okay. And here's the numerical simulation of financial applications. Due to the time constraint, we did 3 parts. One is for the low dimensional to illustrate numerical simulations. Then we consider first to default swap, okay, which indeed first to motivate our research. Okay. Then we consider special case, which is periodic functions. Okay. Okay. Here is numerical simulations. We consider 2-dimensional. X is normal 1, 1, Y is normal 0, 1. Correlation is rho, and here is the boundary. We run crude Monte Carlo as a proxy of true probability with 10,000 times. Here is the boundary. Okay. Here is simulation, means the Monte Carlo simulations. Here is standard deviation for the simulations. Okay. Here approximation is by using our analytic approximation formula. Okay. So boundary is 5, 25, 50, 5, 25, 50. You see, we use this one as a proxy of true one. Okay, here is by our formula. You see the difference is rather reasonable small for the case. Okay, then probably I'll skip this one and consider first. Okay, this is some kind of they call real application, pricing force to default swap. Okay, consider this one. This is d-dimensional. Here is the boundary. Okay. We consider B equals 20, 100, and 200. And dimension is 2, 3, 4, and 20. Okay. Here's the result. Okay. Here you see the expected time does not increasing too much from 4 dimension to 20 dimension. Okay. The reason for this is because we just consider first to default swap. So even the 20 dimension, the first time to hit the boundary is some kind of like low dimension. Okay. So the difficulty might come from the nth to default swap. For instance, we have d-dimensional, the 20. We consider the third one, the fifth one, that might be difficult. Okay. Here we only consider the first one, first to default swap. Okay. Still give us reasonable well approximation. Okay. So the good is to save time. Right? Here we run the crude simulation. This is all run by seconds. So it's very, very fast by using our analytic approximation for probability. Even for expected value, this is a reasonable deduction from 70 seconds to 2 seconds. Okay. Okay. Okay, let's skip this one. Here, a conclusion. Okay. Although this is a classical problems, and we believe we introduce a method. I'm not quite sure this is rather new or not, but it's according to my knowledge, this is a new method by treating simple random walk as a Markov random walk. Okay. Then we hope to provide some useful information for boundary closing, and numerical illustrations support our results. Here is future works. A challenging problem is to consider the variance of tau. And that gives us, and right now we only consider expected tau by suitable choosing the truncation and the boundary goes to infinity in a suitable way. But for this one, oops. Okay. Rather challenging problems. The second one is try to deriving most specific results from multidimensional Q-sign and multiple sensor problems. Here we just do numerical computation for boundary closing by ignoring the slowing change terms. And here some kind of approximation are needed for multiple sensor problems. Okay, last one here we provide a mathematical device by using hidden Markov model, or we call Markov random walk, to simple random walk problems. And we hope these can be used to handle unit-root test in Markov switching models. Okay, that's the end of story. Thank you very much.
This is already an amazingly complicated calculation, but I want to ask whether you can make it even more complicated by considering random walk, where the principal part has negative drift, and so you would presumably use an exponential change of measure, then apply your results.
That's very nice questions. Here, the problem is, I've solved this problem last night because I guess you might ask these questions that are related to your correct diffusion approximations. Yes or no? But here first we need to have exponential embedding for Markov random walk. Okay. Here's the exponential embedding for Markov random walk. Right? That means P I j theta fj of y. Right? You have exponential embedding to the theta y minus lambda of theta. So you have f of this should be theta. J of theta y dij of theta. In order to make this reasonable, I got to multiply by 2 terms. J theta I theta. Okay.
But you might be able to make the exponential change of measure only with respect to the random walk part.
But we handle this one by using Markov random walk. So the first natural way to think about it is to use a Markov chain exponential embedding, yes. Right? So this is log moment related log moment generating function. This is log of largest eigenvalue of the matrix. Okay, this is corresponding eigenvectors. So this is exponential embedding. So the tilting, it depends on the problem. So it's negative drift to become positive drift, so for this tilting. But in your setting, correct diffusion approximation, that means zero drift. Zero drift means to make this as not so real, right? Not so real. So we consider this a moderate deviation tilting. So I have some kind of a theory for this kind of tilting.
Okay.
Yeah, and hopefully can be applied to these problems.
Okay.